All right, so let's do the box on ramp problem, except let's do it the hard way. We'll have horizontal and vertical coordinate system, so just sticking with the brainwashing of positive, positive. So I'm use I hat, j hat. If you use x hat, y hat, fine. I do know the acceleration is going to be in this direction, so there'll be two components there. Since acceleration has components, so I broke it down, and I'm going to make ay a negative number. And so this distance right here, it's down, and the magnitude is negative ay, and the magnitude there is ax. When you actually plug it into here, ay itself will, again, be a negative number because I said up was positive. We can go through the facades process. If you're not familiar with what I mean by that, there are other videos where I do talk about facades, but this is just a step-by-step about how to solve these problems. So first I'm going to deal with no friction. And so we have a force diagram with a normal force pointing away from the ramp and a weight acting down. Since weight is in the negative j hat direction, I need to decompose y, and working out the geometry of it, I have theta here, I have theta there, alternate interior angles. The normal force is perpendicular to the ramp, and so this theta prime here is the complement of theta, and I typically label it as theta prime. And so this angle up here in this part of the triangle, so if I think about this, a triangle right here, this angle up here is theta, so the opposite is the horizontal, and that'll be the sine, and the vertical is the cosine, so y cosine, y sine. My equations of motion, if we go back to looking at our breakdown there, I have y sine theta to the right, so if y sine theta is equal to mass times the x component of a, and then I have 2 in that direction, so I have y cosine theta minus w equals may. Again, I should end up with a negative value for ay if we were actually using numbers. Doing substitution, I am substituting in mg for w, and that's pretty much the only substitution I can do here. Now, I have 2 equations here, obviously, and 3 unknowns. I got y, ax, and ay. Now, I do have a relationship between ax and ay. Actually, I have 2 important relationships. One, for a third equation, I have tan theta is negative ay over ax. And again, going back to my breakdown over here, there's theta, the opposite over the adjacent. And I have, ultimately, I'm trying to solve for a, and a squared is equal to ax squared plus ay squared. It's a 4th equation and a 4th unknown. This is the one that allows us to actually solve for ax and ay. And then I come down to here. So first off, I need to get rid of an unknown. So I'm going to get rid of y here. So I'm going to take this equation, divide by that equation. So y sine theta is equal to max. Divided by this, I'm bringing mg over, so on the right-hand side I have mg plus may, and on the left-hand side I just have y cosine theta. And then I can factor m out to get m times g plus ay. Tan theta is, well, sine divided by cosine is my tangent, is ax over g plus ay. And my mass cancels out there. And I know that tan theta is also equal to this. Cross multiplying, we end up with ax squared is equal to negative ayg plus negative ay squared. And that negative is not squared. It's negative ay times ay, so it's negative ay squared. So that is the part being squared. Bringing x squared and ay squared on one side because that's equal to a. A squared is equal to this, negative ayg. I know again from my other triangle that negative ay is equal to a, which is the magnitude of that side, times the sine of theta. So I'm taking for ay, I'm making that substitution right there. The negative signs cancel out, and I'm left with a squared is equal to this. Cancel, divide both sides by a, and I get a is equal to g sine theta, which is what you do if you do it the easy way. Add one more twist, let's add friction and still do it, because why not? So force diagram, this time I have force involved. I know that y and f are perpendicular to each other, so if my normal force breaks up like this, friction should break up using the opposite trig function. So the horizontal trig function here is sine, so for friction it's cosine because they're perpendicular, and then sine and cosine like that. My equations of motion, very similar to what I did before. I make the substitution for friction. I am going to assume that it is sliding, so I'm not having to worry about whether I hit the breaking point or not. And I know that friction, kinetic friction, is equal to mu k times y, so I make that substitution here. And also weight is equal to mg. Factoring y out and then dividing, I get sine theta minus mu k cosine theta over cosine theta plus mu k sine theta equals this over here. The masses cancel out. For shorthand notation, I'm just going to let s equal sine theta and c equal cosine theta and mu equal mu sub k. And so this just translates into that using my shorthand notation. Cross multiplying, we get this. Foiling, distributing, canceling out common factors, and we are now down to left to this. Here we have a cosine squared plus a sine squared. That's a cosine squared plus sine squared, which is a times 1, which is a. And that basically gets us where we need to be. So ay is g sine theta minus mu k g cosine theta, which is exactly what you get if you do it the simpler way. So a lesson in what happens if you don't try to go for a more convenient coordinate system.